Good morning and or afternoon, everybody. I think it'll be afternoon for you, period 5. Hope you are all having a fantastic day. So last time when we left off, we had been talking about structures of ionic solids, as well as intramolecular force and potential energy, and types of chemical bonds. Today, I want to talk about our other topics: structure of metals and alloys, Lewis diagrams, resonance and formal charge, and finally, VSEPR and bond hybridization. So, let's start off with our structures of metals and structures of alloys. And honestly, this is a fairly simple topic, so it's going to be pretty similar to what you saw in the video, right? Metals are going to be these positively charged particles that are fairly tightly packed, but also not so tightly packed as to have a kind of problem of repelling each other. There we go. Right, and they are held together by delocalized electrons. Delocalized electrons are going to be small electrons, well, all electrons are small, are going to be electrons which are spread throughout the metal. They are delocalized. So what delocalized means is not in one place. And usually what we mean by delocalized electrons is not bound to an atom or ion. In this case, they're not bound to the metal atoms. They are delocalized and they are free moving. This is important and key because free moving electrons and other charged particles is the key to understanding conductivity. A substance conducts electricity when there are free moving charged particles. Electricity is a movement of electrons via potential energy. And it doesn't have to be, it's not like the same electrons moving throughout something, but rather you use potential energy to cause electrons to move, causing other electrons to move. In this case, by applying a positive charge to one end of a metal, you could get the electrons to move over. Actually, let me use a different color here. Oftentimes positive charge is represented with red, so let's use red. Right, you can get a positive charge applied to the end of this that cause electrons to move, and at the end result in a negative charge on the other side. This is actually one way we can measure charge, right, is causing electrons in a metal to move from one side to another. This creates a potential energy difference where the electrons are more concentrated on one side, right, making it overall a little bit less stable, just a little bit, it gives it a higher state of energy, and you have a big difference between one side with a bunch of electrons. Sorry, this leaves this side being more positive. I apologize. It leaves this side being more positive as this bit becomes negative to counteract it. Now here's the thing, right, even though there's two positives, this one's going to be a bigger one because it's going to be an external positive. So it pulls all of them this way, gets negative, right, leaving this side positive. My apologies. So this potential energy difference here and here is what is causing the conductivity. And that's really what electricity is. It's a form of potential energy. This is similar, but not exactly the same, to ionic compounds. In an ionic compound, right, you're going to have this lattice energy. And when you have a solid, these cannot move freely around. So they're kind of stuck where they are. However, if you were to melt an ionic compound and make it a little more fluid, sorry, this thing does not want to go in. Oh, come on. I got this. There we go. Here we go. A little more fluid and a little less uniform. Right. Then these are now free flowing. Because again, liquids don't have a set structure. All liquids can move about freely. Once these can move freely, they can also conduct electricity. Last version of this is actually a solution. A solution of an ionic compound has ions, or has rather compounds that dissolve and dissociate, right? So you don't just have sodium chloride. You have sodium and you have chloride. And since they are in liquid, they're freely moving around. Right? This, again, enables conductivity. So if you try taking physical salt and conducting electricity, it won't work. But if you try dissolving salt in water, it will work. This is actually why pure water does not conduct electricity. Right? It has no charged particles. So pure water will not conduct electricity, but the only way you can really get pure water is in a lab. That's really everything there is to say about metallic structure. It's, at least for the scope of this class, fairly simple in that regard. It doesn't go beyond that. Again, here's a bit about conductivity that you should definitely take note of. You might get questions looking at a solid, right, and the ask if it's conductive versus a liquid ionic compound or a solution. Let's also talk about alloys real quick. Alloys are another one that are a fairly quick compound, or sorry, fairly quick topic. We have two types of alloys. We have interstitial, where did I leave that off? Interstitial alloys, as well as substitutive alloys. So interstitial is a word that means space between. For example, another place we see interstitial is interstitial fluid. Interstitial fluid is a fluid that is found in the spaces in between cells. Right? This is the interstitial fluid. It helps stabilize cells. As well as, right, see here, bring oxygen, nutrients, and remove waste products. But this isn't biology, and I don't really remember what it does that much. Interstitial fluid is also in your ear, and your body uses the interstitial fluid in your ear to tell if it's balanced or not. So, as a quick aside, the reason you start feeling sick if you spin around too much is that the interstitial fluid in your ear that your brain uses, again, to basically orient itself, gets shaken up a lot when you spin around quickly. And as a response, your brain is trying to process what's going on, and it makes you feel sick. So that is the reason why you get dizzy and sick from spinning around. So, interstitial alloys form alloys in the spaces in between atoms. One of the most common examples of this is steel. Right? Let's take a look at our periodic table for a second and compare the sizes of carbon and iron. Carbon, let's look at the properties, right, let's find our radius, 67 picometers, whereas iron is 156 picometers, so almost 3 times the amount. Because of that, and we tend to draw them much smaller so we can tell the difference, but because of that, right, when we have our iron combined in our metallic structures, right, there is space in between them due to the natural spacing of the larger chemicals. Right? It's not like a square that can be packed in very easily. There's always going to be space there. The carbon atoms, right, the carbon atoms go in between those spaces. This means you won't really see too big a difference between density of one metal and density of the other. So for example, density of iron, 7.874 grams per centimeter cubed, versus density of steel, 7.85 grams per centimeters cubed. Right. So, and stainless steel has a bit of a different density because stainless steel has niobium in it, which is bigger. And I believe stainless steel combines the substitutive and the interstitial. But let's check that. Let's say stainless steel structure, chemical structure. It is, if we can find a good structure of it. If not, that is okay. I mean, I know there are more pipes, right? Because there's nickel. I'm pretty sure it is niobium in it. Well, can't find one. I'll see if I can find one in between class sometime. This was more of a spur of the moment thought. Substitutive alloys come from alloys that are similar, or metals that are similar in size. So we can look up just to show you an example of this. Right, sorry, substitutional, not substitution. Should be a good example of an actual one here, and not just images, though. It's going to be things that are typically larger. I believe brass is a good example of this. But again, I'll find those later, and I will send the pictures. I'll post the pictures of the classroom with the lesson. Sorry, I will get back on track. Essentially, what you're going to see is, and it's not necessarily going to be perfectly ordered you're going to see, oops, occasional, right, replacements here and there. Right, of atoms that are approximately the same size. So again, an alloy of any two atoms that have about the same length will be a substitutional. Let's fix that. Oops, sorry. Substitutional. That's pretty much it for alloys, as far as alloys are concerned. So, with that in mind, let's do a couple practice problems for that, and then move on. Right, and these are the practice problems I previously had you do. As we get into the next week, I'm going to be asking you to do these practice problems and videos the night before as homework. So, copper and zinc atoms have the same atomic radius. Based on this formula information, which of the following diagrams best represents an alloy containing only copper and zinc? So let's go through and see why each of these are right or wrong. So first off, with the same radius, we are going to be looking at, right, a substitutional alloy. So this one is an interstitial. The second atoms are placed in the spaces in between the larger atoms. B, however, is substitutional. We see that some of our white atoms are just replaced by our gray atoms, assuming it's the gray ones that are the substitutions. We don't really know, however, but that doesn't really matter. One of them is a substitution, one of them's not, and they are approximately evenly dispersed throughout. They don't have to be the same amount. That's going to depend on the percentage of the alloy. Now we look at this one. This is an ionic solid. Alloys won't have positive and negative particles, right? All the metals will be a little positive and the electrons will be floating around freely, but that is not the same as positive and negative particles. And finally, this last one, they are all the same element, or at least we can assume so based off of the color. Therefore, it's not an alloy, seeing as an alloy is a combination of two or more metals. Let's keep going. This is a particle level diagram of a metallic element. Metals are usually malleable and ductile. A quick refresher what that means. Malleable means it can be shaped. Think forging and blacksmithing, right? Whacking it with a hammer to shape it into a different, well, put it into a different shape with force. Ductile means that it can be drawn out into a wire. That is a unique property to metals. So, the best explanation for these properties is that the electrons involved in bonding among the metal atoms are, and we look at our options, unequally shared and form non-directional bonds, unequally shared and form highly directional bonds, equally shared and form non-directional bonds, and equally shared and form highly directional bonds. So, for this one, right, there's one thing that we should note about malleability and ductility. If something is malleable, that means, again, it can be shaped. That means that it's not particularly frail due to being hit in any general direction. However, right, we also have, in addition, we have our ductility. It can be drawn out very thinly. This would again speak out against highly directional bonds. I'm going to finish this one in just a second. I just need to run and grab a drink of water, so I'm just going to turn off my camera for 1 second, and I'll be right back. Sorry about that, everybody. Just had to grab a quick drink. So, I want to talk about, the now even and uneven sharing of the electrons a bit. The electrons are going to be equally shared. The reason we know this is, again, there's no particular part of the metal that is going to be extremely frail and fragile. It is being held together everywhere. In addition, because they are positive particles, the electrons are just going to spread them out. It is a C, they are constantly in motion, but on average, they are going to be evenly dispersed. So we are looking for equally shared, non-directional. All right, our last one here. Steel is an alloy containing iron and carbon atoms. Which of the following diagrams best represents the particle level structure of steel? You don't need to know the exact size of iron and steel to know that iron is going to be significantly bigger. It is several places down on the periodic table, right? We have it carbon here, we have iron all the way here. In addition, iron has the d orbitals, which are going to be even bigger. Sorry, they're not going to be significantly bigger because they're still the 3d orbitals. My apologies. I was thinking of the 4d orbitals. But either way, right, we are looking for one where iron is bigger than carbon. That already tells us one answer. B. In this one, they're the same size. In this one, iron is smaller. And in this one, you have some large and some small irons, and some large and some small carbons. This doesn't really make sense, as all atoms of a specific element have the same radius. So, we're looking at B as our answer. All right, let me look at the time here. 24 minutes, okay. So, let's keep going and try to cover everything. I might end up having to do a third day of this, although I would prefer not to. Lewis diagrams are review for you guys, so this should go pretty quick. Lewis diagrams, remember, you start off with a formula. So, for example, CH4. You take the least usually you take the least electronegative metal element and put it in the middle. However, hydrogen can't do that. So for this, typically though, if you have carbon, carbon is in the middle. We have carbon. And then we simply attach all of the hydrogens to it until we reach 4 bonds. In this case, since we only have CH4, hydrogens always go on the end because hydrogen only has the 1s electron shell, which means it can only hold 2 electrons. Which furthermore means the most electrons it can have is 2, and so it can only have a single bond, nothing else on it at all. Because every element has to be bonded to another one in a molecule, hydrogen will always have 1 bond and therefore will always be on the end of any molecule. You will never see hydrogen in the middle. Now, for more complicated ones, we have a longer process in which we count out our total number of elements. So for example, NH3. Sorry, it's the most electronegative element that goes in the middle. Actually, no, scratch that. It can depend. So ignore that. Usually it's the most electronegative. Except sometimes with oxygen. Oxygen does like to go in the end. And carbon pretty much always likes to be in the middle. Carbon loves being, it's really the backbone of many different molecular structures. So we have NH3. At first glance, it's tempting to write NH3 as this and call it a day. But we have to make sure of a few things. One, the octets of every element are fulfilled. And 2, every electron that we have access to is used. This does not have a charge. This means that it's a molecule. So each valence electron of each atom is going to be what's making up the electrons we work with, without any more or less. Nitrogen is in group 5 on the periodic table, so it has 5 valence electrons. And hydrogen is in group 1, so it has 1. 3 times 1 equals 3. We have a total of 8 electrons to work with. So then we draw our skeletal structure like before. We choose one element to go in the middle. Again, often this is going to be, you can usually tell what element it's going to be by looking at it, especially when hydrogen is involved. They're always going to be on the end. Oftentimes it's the element listed first, except in cases like water. And oftentimes it's the element that you have 1 of. That's another big hint. Again, you can have multiple carbons though. None of these are sure rules that always work, but they are quick rules that might give you the answer quickly in many situations. So we have 8 electrons to spread out. We've made 3 bonds, so we've used 6 of them in total. All right, we are left with 2 electrons. Now we can check how we've fulfilled our octets. 2 electrons, 2, and 2, the maximum that hydrogen can have. All of them are satisfied. However, from these, nitrogen has 2, 4, 6. It would like 8 in total. So we have 2 more electrons we can put directly on nitrogen. This is called a lone pair. A lone pair of electrons. I'm going to do one more quick example. NO3 minus. NO3 minus is what we get when we have, well, when we have a charge, right, we adjust our total number of electrons based on that charge. So normally for nitrogen we would have 5 electrons, and for each oxygen we would have 6 for a total of 18. This would give us a total of 23. However, with a 1 minus charge, we have plus 1 additional electron, which brings us to 24. So now we can draw our shape. We have 1 nitrogen, so we'll put that in the middle, and then we'll put our oxygens out. Now, after this, we want to and this is the first one we have without hydrogen, so this is another good example, we want to fill the octets of our outside elements first. They're not going to be bonding to anything else, though. We don't have any more atoms to bond to. So we will fill them with lone pairs of electrons. This used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. We've used up every single one. However, we still have a problem. Nitrogen. Nitrogen only has 6 electrons. So we need to give nitrogen access to 2 more. We can do that using our lone pairs. We can take one of the lone pairs. Oh boy. And turn it into another bond called a double bond. Ignore that. This double bond gives oxygen and nitrogen access to the electrons. It's also stronger than a single bond and shorter than a single bond. We also have triple bonds, which are even stronger and shorter than double bonds. So let's run through the problems for this chapter really quick. Again, I'm trying to go through this one somewhat quickly as we did cover it last year, but you should also be able to go back and watch it as many times as you would like. Oh, they're right, there were no problems with this one. Instead, they're lumped in with resonance and formal charge. So let's get talking about resonance and formal charge while we still have time. We have about 15 more minutes. We might not get to Vesper today. That's okay. Vesper is a bit of a long topic. I can cover that next time if need be. Or maybe I'll make a slightly longer video, finish it for homework. So, resonance. Resonance structures is all about alternate forms of Lewis structures based on movement of electrons. The classic example of this is a chemical called benzene. This is a benzene ring. Each of these corners are carbons. They are all attached to a hydrogen. I'll let you get the picture. Oops. They also have double bonds here, here, and here. However, there is nothing stopping the double bonds from being here, here, and here. Because both sets are possible, both sets occur, and at any given moment, benzene is a combination of the two, changing back and forth. So really what this means is the overall properties are less like a single and a double bond, but are instead more like a 1.5 bond. And actually, you can calculate bond order by adding up the numbers of pairs of bonds or pairs of electrons in the bonds over the number of bonds themselves. So if we look up and we say, okay, well this is 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs of electrons over, counting a double bond as just one bond, 1, 2, 3, 4, 5, 6 bonds, it has a, call it, bond order of 1.5. This can only occur for things that have resonance structures, but it has a bond order of 1.5, again, which means these bonds are more like 1.5 bonds. It is longer than a double bond, shorter than a single. All of them, right? They are also stronger than a single bond, but weaker than a double bond. So it creates interesting properties of these chemicals. Oftentimes, later on in more advanced chemistry, resonance is one of the major reasons behind certain reactions. We also see resonance with our polyatomic ions, so the one I just had before, NO3. We have a double bond here, a single bond here, and a single bond here with all our ions. But there's no reason that these ones couldn't form the double bond instead. And so what you get is, I'll just leave out the electrons. What you get is 3 different structures for NO3. So if you want to do a bond order, you would say, okay, we have 1, 2, 3, 4 pairs of electrons split up between 3 different bonds. 4 over 3 is going to be, right, 1 1/3, or a bond order of about 1.33, repeating. So these ones are not as strong as the benzene bonds, the 1.5 bonds, but they are longer than them because they're closer to being a single bond than they are double. Now, keeping up NO3, I'd like to also talk about formal charge. I'll redraw it up in a second. Formal charge. Formal charge is all about counting, looking at the number of electrons directly on an atom, say on average, compared to its protons. Or really just compared to what it normally has. You don't really need to think about the number of protons. So let's talk, for example, about NO3. Normally, oxygen has 6 electrons. It's in the 6th family, 6 valence electrons. It's in the 6th family, so it has 6 valence electrons. And we know in total it has 8 electrons, but 2 of those are on the inner shell in the 1s orbital, and those are canceling out 2 of the protons. There are 6 protons canceled out by the 6 valence electrons. However, if we look at this oxygen, we see it has kind of a different number. Now, in total, it has 8 through covalent bonding, but these aren't going to always be on nitrogen. In fact, when we talked about how the fact that they technically aren't due to polarity, for formal charge, we assume they are evenly shared enough to cause this effect, which we measure as accurate. So we can count 1, 2, 3, 4, 5, 6, 7 electrons, giving oxygen 1 of the electrons from the bond, because you would think on average it will have 1 at any given moment. With 7 valence electrons instead of 6, we're left with a 1- formal charge, which means it's the same over here, since this is the same oxygen. Well, the same structure. Now we can look at this oxygen, 1, 2, 3, 4, and it has a double bond, so it has 1 from each on average. 5, 6, it has the same number. so it has a formal charge of 0. And finally, we have nitrogen. Nitrogen, getting 1 from each bond, gets 1, 2, 3, 4. 4 valence electrons. Nitrogen is used to having 5. So if we have 4, that means the nitrogen has a 1 plus formal charge. Let me just check our time real quick. Alright, we'll probably have to wrap up after this, actually. So a 1 plus formal charge makes sense here. The 1 plus and 1 minus cancel out. Nothing cancels out this 1 minus, though, leaving NO3 with an overall 1 minus charge. You can actually identify the charges of polyatomic ions using this trick, although you'd have to know how many electrons they have to start, which requires the charge anyway. So, maybe not. Alright, let's go back and go over a few of these questions, especially as resonance and formal charge are difficult topics. So, after this, we'll probably call it a day. This is the benzene ring I mentioned before. They just have all the carbons and hydrogens drawn out. So we can see that we have double bonds and single bonds alternating. Right, so we are saying, what claim can we make about this? All the bonds between the carbon atoms have the same length. Because of the variable bonding between its carbon atoms, it's a good conductor of electricity. Well, conduction of electricity has to do with movement of charged particles, which this doesn't have, so we can rule out B. The bonds between the carbon atoms, C6 and H6, are unstable, and the compound decomposes quickly. There's no evidence whatsoever that it's unstable. In fact, this is actually one of the more stable structures in chemistry. But you wouldn't have any evidence of it being unstable just based on this. C6H6 molecule contains 3 single bonds between carbon atoms, 3 double bonds between carbon atoms. So this would probably be the second best answer and the best one to go with for being wrong, right? Because at least you're looking at this and, not just going with some stuff that's more nonsense type, that doesn't make sense if you think about it for a minute. And if you go for these ones, that's all right. If you're really feeling really tripped up, it's easy to go for the wrong things, but usually in retrospect, right, 2 of the answers for each of these will seem pretty obviously wrong. So this one is just requiring you to recognize that resonance structure means they're all the same. So our answer is A. Now we have the following Lewis diagram best represents the bonding in the N2O molecule considering formal charges. You want to minimize formal charges. You don't want like a +4 and 4 -1s, because that +4 is really unstable. So let's look through and figure out which ones are possible and which ones are not. For an N2 molecule, we should be expecting let me try to load that up again. That doesn't want to go. I will open the pop-up. Nope, okay. Well, let's clear everything and try writing over here. All right. We have 2 sets of 5 plus 1 set of 6, 16 valence electrons. So first off, without trying to draw the structure ourselves, let's see if everything fits this. And we can quickly notice this one does not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 valence electrons. This one is impossible. It has too many electrons. In addition, this one doesn't fill the octet rule of oxygen, so it's also not possible. Now let's look at what remains. We have 1, 2, 3, 4, 5, 6 on oxygen, giving it 0. 1, 2, 3, 4 nitrogen, giving it +1. And 1, 2, 3, 4, 5, 6 on nitrogen, giving it -1. So here we have a neutral oxygen with the nitrogens canceling each other out. Here we have 1, 2, 3, 4 on nitrogen, again a +1. 1, 2, 3, 4, 5, 6, 7 on oxygen, a -1. And a 1, 2, 3, 4, 5 on nitrogen, giving it a formal charge of 0. This one might seem like you can't be figured out at first. until you remember electronegativity. Oxygen likes having electrons more than nitrogen. So if anything is going to have the negative charge, it's going to be oxygen. That being said, this is actually, well, both are possible and plausible, and both probably exist. But instead of the benzene or the NO3 ones where they're all kind of equal amounts because they're really all the same, these ones you probably have the vast majority being this, and you have a small percentage being that. Just by chance. This can take on a negative charge, and that is zero charge. It's just less likely than that. Which also is why we ask for the best representation. All right. Let's do this last problem and call it a class, as we're just about at our time. And actually, this last problem might be... let me see. Let me see if I can... Very sorry. I'm trying to get this to close out, and it does not seem to want to. There we go. This last one asks, which of the following statements, if true, would support the claim that NO3 ion, represented above, has 3 resonance structures? Well, let's look. And actually, I'll start at the bottom, because the top one is right, but one of the bonds is shorter than the other. If it has 3 resonance structures, all the bonds would be the same. One of them is longer than the other. Again, wrong for the same reason. The oxygen to nitrogen to oxygen bond angles are 90 degrees. This is not true, and you actually would need to know Vesper for this, so I apologize, this is a little early, but you can actually just kind of think of it common sense-wise. Why would they be 90 degrees apart, right? If anything, they should be evenly spread out at around 120 degrees. And finally, well, you might not know about the other one. The one that does make sense is NO3 as a non-polar species. If something is non-polar, that means all of the bonds are the same. In order for all the bonds to be the same, when we see one double and 2 singles, we must have resonance with every bond, with the double bond being able to be on either 3 of these. So it would be A. All right. Next time, I'm going to try to go through Vesper and bond hybridization, and then I'm going to try going through the project check problems. If you don't already, please have the project check done by the time, well, really by next class. It's only 15 problems, it doesn't go for that many. And the open response, do your best on those. I know they are tricky. Again, these are AP questions. You're not designed to get everything right. If you are getting, for these ones, they're a bit easier than AP questions, but not by much. So if you're getting like 60 to 70% right, that's a really good sign. Well, I'd say they're about on par, like slightly easier. So again, shoot for like 60, 70% of it correct. Try to just be above 50%, right? That should be your goal. All right, have a great night, everybody. A great day, but well, also night, I suppose.